So last time we discussed about memories, right?
Yeah.
So we discussed till now the dual port RAM, basically DP RAM. Okay, and we discussed about how we can infer different types of available RAM in the FPGA, right? So you don't have any doubt, right? Like how based on the coding style we can infer.
Mm.
Okay, so today we will talk about single port RAM. Okay,
Mm.
single port RAM, and we'll focus on the bidirectional. Uh, First, we'll write the and like input data and unidirectional bus basically. So unidirectional data bus where the data will be separate and data out will be there. And then we'll focus on the this is unidirectional and then bidirectional will be like data in out. Okay. So these two will focus and then later we'll talk we'll try to write the ROM code. Okay. These three things will focus.
Mm. Okay.
So, uh, so as we remember, like yesterday we discussed, the single port RAM will be having the ports like clock, data in, then enable, and write or read. Basically, one command from that we can determine it's a write or read. So they will not, like, they'll be mutually exclusive, write and read. So both will not be happening together. That's why it's called single port RAM. Okay, only one port is there to access the memory at one time, and then data out.
But that is the bidirectional, right? That data in that.
No, no, no. One port means like access port, which is like I want to say,
So read and write, that is only one direction.
yeah, So address, read, write, and address is only one port,
Okay.
not two port. Address also. Okay, so that this is called single port. So what is two port? Like basically we will be having two write, read enable, and then two data in, or basically two addresses. That is called dual port.
Mm.
Okay. When there is only single address to access memory, it's a single port. Okay. This is SPRAM basically because a single address is there. So let's code it. Launch. There you go. Let's create the project. We call it single port RAM, SPRAM. This is again in the memory. So we can have in the same project, we can have same folder, we can have multiple projects also. Because we are doing the create project subdirectory, so it will create its own subdirectory and do there. We are having ports.
In the simulation and the design, what is the difference in that? Simulation sources we create generally, right?
So simulation sources will be like what will happen. Let's say simulation sources like let's say design source is the tool will do synthesis only on the design source. Okay, it will not do the synthesis on the simulation source. So let's say you do add source and you create a test bench also using the design source. So what will happen? The test bench will be part of the design and then it cannot synthesize it. Okay. So that's why whenever we want to create the test bench, we make it a simulation source so that the it is only for simulation it knows. So that it differentiates between the design and the test. Otherwise, how tool can differentiate between the design and test bench if we don't specify which is test bench and which is design. Okay.
So the test bench is a part of that simulation source.
Yeah. Part of simulation. Not just test bench. All the code is part of simulation source, but except test bench, everything is design. And all and in simulation source, everything will be simulation, including design also.
So this design we can also put in the simulation, right?
It's already correct. By default it will appear in both places, right? If you
Okay.
create a design, it will appear in both. If you just create a simulation source, it will only appear in simulation.
Okay. Design also gets in the simulation.
Yeah.
But we can also do in the simulation also, right? The this thing you're writing it now.
It is
No.
same file. It is same. There is no two files. Its file is same. Yeah. If I double click, it will open same file.
Okay.
It's just it's referencing two different location, two different basically. Okay. Then we have address, single address. Right? Earlier we saw like a right address. Here only single address. and the single address is, again, we are taking 256 deep, so let's say will be 8 bit. Data we can take 31, that's 32 bit. And data out. One more thing, like usually the usually the single port RAMs are not available. I mean, basically, the FPGAs are always having a dual port RAM. Okay, so if you specifically creating a source code for the FPGA, then you will try to use dual port RAM always, right?
Okay.
Because but what happened, like you will not be just FPGA engineer, right? You'll be a hardware engineer, right? So in that case, you must understand a single port memory, okay? Because single port memory is smaller than the dual port memory in size. So when once you are writing the code for ASIC, so you will try to use the most of the time you will be using the single port memory,
Okay.
and that's where you should understand how to interface the SPRAM uh, in the ASIC. Okay,
Okay.
but on the FPGA it will always be a dual port memory available.
Okay.
And in ASIC, if memories are hard macro basically, so it is generated by the memory vendors, and they provide you the tool from where you can generate the memory, and you just instantiate the memory and use it. You don't write the code for memory in the ASIC. Understand?
Okay. It's already like.
Already this kind of memory will be available with the similar ports. Okay, and then you just use it
Okay.
in the ASIC. But in in FPGA, definitely you have to code it to infer that what kind of memory you want from the FPGA.
Okay. So if
Even yeah,
so on FPGA, if I design some type of memory and I want the same thing on ASIC, so is that
yeah.
possible?
So that's what you will do. Yeah, it's possible. So what you will do, you will write some generic here. Okay, I can guide you. Let's say you remember generic I said, right?
Yeah.
Generic. Okay, generic you can say integer, type integer, and then you can say what is, and then gen integer, and you can initialize a value. You can define this as a like mem type, memory type. Okay, and then sorry, generic mem type is generic name, and that value you can initialize a value as 0 or 1. Okay, and you can say like 0 means FPGA, and 1 means ASIC. Okay, so let this generic be there. I'll tell you. Okay, later how. So basically you can declare type mem is array, Now I can say generate. Okay, remember generate, generate, and if mem type is FPGA. Okay, if mem type equal to 0, then else 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 we can say it's yeah, let's Google it. We last time coded for generate. If generate is also there, or if generate like this. Sometimes it's in Verilog basically we write first generate and then we write if inside it. So that I get confused between Verilog and VHDL. So Verilog is this type and VHDL is like if generate, and then I think end if won't be there and generate directly. Okay, and generate. So we write like this. Okay, if I still error. Maybe label is also important. So we can say FPGA. Is it really label issue? Yeah, label issue. Yeah, now this. So if we can write like this, if so we are writing FPGA type. Okay, so we can write any code here. It will be when it is 0, it will implement this code. Okay. Otherwise, we can write something like this. If we can say ASIC, and then mem type 1 we are defining as ASIC, so we can say ASIC. Okay. Okay. Yeah. So whatever we write here, it will be like the ASIC. So here in ASIC, whenever you want to implement ASIC, right? We can say I'm just writing a comment here, right? Instantiate ASIC SPRAM. Okay. So what will happen? Like we will write here. We'll write a component here, right? Component for RAM or ASIC. Okay. And here you do instantiate means port map, right? Basically, you create a component and add the port map. So So when you instantiate here, but basically you'll by default you write both code, and based on the generic, it will when you want to take the same code to the ASIC, it will implement the this type memory. Okay, basically it will replace this will not be created. It will create the memory of whatever you instantiated. Otherwise, when you select FPGA type, it will create this memory.
Mm.
Okay. So this is how like you can write a code for which will work on the ASIC and as well as on the FPGA. This will also work on the ASIC also. This code also because it will create ultimately it will create the registers in the ASIC
Mm.
whatever you write. So it will still create, but it will add to the area which you don't want.
Okay.
What will happen like the same code will create a memory hard memory in the ASIC, right? If you or in the FPGA, right?
Mm.
It will take the dual port memory from the FPGA. And you remember, I showed you three different type of memories can be shared based on the coding style. But
Yeah.
but in ASIC, it will always implement the register based memory if you use the same code. It doesn't understand for the ASIC. Okay, it will understand only for the FPGA.
So
Okay,
ASIC is also like similar to FPGA in terms
all
of.
three code will yeah all no in ASIC all three code will implement always a register.
Mm.
Right? So whatever three types so that all three different types will always create a register only in the FPGA in the ASIC only.
Mm. Okay.
Right. So that's why we don't want to create a register for memory, right? In ASIC, so we take a hard macro basically. We say it a hard macro, and the hard macro will be instantiated. So basically, what happens like you remember you must have studied layout, right? In electronics, you would have some subject, right? You create a layout. You know, remember?
Like layout for the PCB design.
Not PCB design, the gates,
Yeah, in the
register layout. You remember?
no, I had VLSI, but I don't
Yeah,
remember
yeah.
exactly now.
Okay, so basically, it's like a uh, there's a there's a tool is there like which is spice that creates if using that spice you create a like basic cells basically. So
Mm.
what we are writing here code, right? Ultimately, what will happen? It will go and create some cell, right? A gate cell, flop cell, right?
Yeah.
And that cell, how it will look like? Who designed that cell? So that cell is designed by the basically the layout engineer,
Mm.
or we can say the foundry, like you know TSMC, right?
Yeah, yeah.
Yeah, TSMC, Intel. These are and global foundries. These are the foundries which manufacture really the chip, right? So they design the cell basically each cell, how it will look like, and that each cell is depending on the technology. Like we remember, I mean, you know, right? 3 nanometer, 5 nanometer, 10 nanometer, 7 nanometer, or 15. Yeah, you know, right? This
Yeah.
technology.
Yeah.
So 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 basically that is a like gate length. So gate length is like you remember transistor is always having a gate, right? You go to
Yeah.
street, yeah, yeah. So that gate width defines the technology. So how small gate you can design that become the technology node. Okay. So using that technology, somebody will like some third party will design the optimized cells. Like that, the memory cells also some guy will design. Some memory companies are there, they design the memory cells also, which you can which implementation guy which is implementing the source like VHDL code or Verilog could directly use that cell instantiate basically. Okay,
Mm.
so what will happen? The tool will not find any code for that cell in the while doing the synthesis. So it will look for the look for the cell library. It will look for the library, cell library basically. When doing the ASIC synthesis, it will look for the libraries, whether that cell is available or not in the library. So and that library is provided by the those guys like TSMC memory, ARM memory. They will design the memory. So we will use those memory using the libraries. And how we use that memory library using the port map.
Okay.
Basically, we don't create the memory using the flip-flops in the ASIC. We can create still we can create the memory, small memories using flip. Told you, right, a small memory like 16 location, 32 location is very small, right? So that may take a smaller area on the chip compared to the because those small size memory will not be available also. Nobody creates so small memory. Okay.
Okay. So instead of that, what is there, like registers, you said?
Yeah. So you will then you will code it. So you will code it the memory instead of creating using the wrapper using the component. So either you can code it there also, but it will always be a register there in the ASIC.
Okay.
Okay. Reset we don't use it the memory. So we are creating, let's say, dual RAM only. Okay. So clock if enable. So two condition, right? If enable equal to 1 and and write read is 1. Okay, then it's a write. So we say so write means like we have to create the signal also, right? It's a type mem. Okay. SPMem. Basically, we write to the SPMem, right? SPMem convert underscore integer. Remember, like we cannot give uh, vector. We have to give integer value. We cannot give a standard logic. And this will give error because we are not using the library. Library. The write is done. Now we read it. So create a process. Same process. Enable equal to 1 and then this is 0, right? That time we read and this will be a data out. Same address, right? Data out. So you'll be thinking like there's just a difference of address, right? And read enable, separate read enable. So do you think it will create a separate, different hardware on the FPGA? We can try. Okay. I think it will create the same hardware because there's no single port kind of thing in the FPGA.
Okay.
So we'll just run the simulation. We'll see it will be using the DP RAM. Block RAM basically. We say BRAM, right? BRAM is a block RAM. Block RAM is always a dual port. So whatever you write, because it does not matter what address you are using, it is a coding style. Coding style is like you are using an address and you are using a enable, which then it will always have a block RAM. And for your perspective, like you are using a single port. So why you can say like why it's needed like because in FPGA in ASIC is needed. That's why that's how we write it. Okay,
Mm.
let's see the report. I see block RAM is still the block RAM, same, no change. Even the DP RAM you do or SP RAM you do, it's always a block RAM in the FPGA.
Mm. Okay.
Okay. So let's do the simulation. Okay,
Mm.
we create a source simulation source basically. Let's say I'll show you if I add source and I create a test bench. Create file AB. Okay. I am creating design source as TV. What will happen? Like it will create a design source in this only here, both places basically.
Mm.
So what will happen? Like here also it created, and whenever we do synthesis, right, it will give error for this because it is here also, and we cannot synthesize a test bench because we are using no ports in the test bench. We are using initialization and all. A lot of things which is not synthesizable, we are using the test bench, and it will give errors. Okay, the wait statement we are using. So that's why whenever we have to create a test bench, we always create a simulation source, so we can remove it.
Okay.
So now we create a simulation, so add source. We already created it, that file, we can add it. Whatever file we are creating, it will always be in the source.
Mm.
So here we created it, we are adding the TPS. Already created it, so we are just adding. So now I added as a simulation. So added simulation is right. Why should we just remove it? Oh, I added as design source. I add as a simulation source. Okay.
Mm.
So now it's only in the simulation. Eh?
Mm.
So I can take this. You can say like why I'm simulating this is similar to DP RAM, right? But I want to show you after this we'll modify as a like bidirectional, the same code. Okay. Yes, there is a clock. Anyway, reset we are not using. No problem to have a port. It's okay, but we are not using it. And then enable is also 0 initially. Okay, clock. So clock is always. So now you'll be remembering, right? We are so creating so many times clock.
Hmm.
Not needed actually. Reset will not using. Not using it. We'll leave it. Then wait, right? Wait for 10 ns. Same thing we can use. And this time B address. And then again write. Okay. Then we do read. Let's change the data here. D1, D1. And read to read it should be 0. Okay, and we read C address. Okay. And data in is anywhere there does not matter. We have to create a component also, right? Port map basically. DOT. So since we are reading generic, right?
Hmm.
So let's mem type is let's uh, pick 0. Okay. Port map. Generic map. Oh, it's not integer. We define integer, right? Let's check the type. Okay. So let's add the duty signal also. So duty like memory we want to add, right? SP mem. We can read that. So you see, First it is writing C here and C location and then B location, right? And then we are reading, right? So this time it was a two writes was there, okay, then one read, okay, and then read was on C location. So you see, we read so C location was 5 5, the 5 5 data, okay. And it's doing in the loop, right? So basically the process, you remember, it it
Yes.
comes out of here and then goes again, so it will keep executing the same thing. So that's why it is repeating the same thing, CB, okay. So this you understand, right?
Yeah.
So now we'll understand the bidirectional bus, okay. So bidirectional bus, you remember I said
Bidirectionality is a tri-state. Zero
SP
one.
RAM bidirectional bus. So it will be basically how we represent it. Everything will be same, okay. Clock reset won't be there. Any no need of reset, okay. So here will be like data, okay. We can say data, and we represent bidirectional like this, okay. And this will be write read, and it will be yes, we can still okay write read, and what else? Address, okay. And enable. So only so you see now data is only having one port. So I remember, right, as you said, right, last time I said, right, I said this is a bidirectional bus. So there is like a this is like a driver from outside, okay, and one driver from inside. Okay, so how it is driving? So this is like a write data basically. Somebody will be writing the driving the write data on the bus, okay, and how it will driving whenever it's a write or read, okay. The write is there when this is one, it will enable for the write data, okay. It will driving the bidirectional bus. So whenever it will be when this is one, it will enable it. Otherwise, it will drive the high impedance. Okay. So when write reads equal to one, then the here it will be write data. Okay. Otherwise, when this is zero, it will be high impedance. Okay. And similarly here, there from internally also there will be a tri-state buffer, and this will be using the not of write read. Okay. And this is like a read data. Okay. So how it will be like this guy, internal guy will be whenever read write means like whenever it's a one. When it's a one means it's a write. So so it's a not is there, right? Basically this will when this is one, it is making is disable. So disable means it will drive Z here. And whenever this is one, this is zero, it will drive read data. Okay. So it is this is difference between the read data. Okay. So let's code it. Okay. So we'll use the same code, okay, and we'll just update it. No need to preserve the old code, right? And it is very simple, okay.
Okay.
So according to this, we remove this, right? Data in data becomes data, and its type must be in out, okay, and rest is same, okay. So this test bench, right, and data is not there, okay, and this is also
The data out, do we need the data out?
The data out we don't need. And in SPRAM, similar modification data is not needed. This will become in out. Okay. This is needed. This is. Do you think this will work?
Yeah, I think so.
This will not work. You see the simulation. Now there is no compilation error, but simulation will not. It will give it will give a multiple driver. Okay. And the data port, right? It's not working. It's a U. So basically, some multiple drivers are there. Okay. How multiple drivers are there? So what is happening, right? Where we are taking the data in the memory, right? So when we are so basically what will happen, like this data we are writing, right? Or let's add the test bench data also, right? What is the test bench data? Okay. See, is also U. You see, even though we are writing in the source code, uh, we are writing the data, right? We are, but nothing is appearing on the data, right? Address is changing, everything is changing, but data is still U. Understand? Why? Because there is a multiple driver here. What even multiple driver? Multiple driver, multiple places it's driving. Two drivers are driving the data on the bus same time. So why same time? Because we are driving here, okay, and here also we are driving from inside, right? Data same. So same bus is connected, right? Workplace, and we are driving same time. Two different thing
Okay.
on the bus. So it is contention. It's called contention. Okay. So it will give you a U or X, whatever. It can give you an undefined thing. It does not know what it will come. Okay. And let's do the synthesis. So synthesis will also give you error. Synthesis may not give error because we are just synthesizing the this, right, this part. So it will not identify multiple driver. But if let's say TB was a design, then it will identify that driver, multiple driver. Why it cannot identify multiple driver synthesis? Because synthesis is seeing only this source, right? Right?
There is no
Synthesis is not seeing the TB. So here only one driver is there because only data is driving by this. So synthesis will not identify it. But let's say TB was a design kind of thing, one more hierarchy for design, then it would have identified uh, warnings. Signing warning is there. There is no warning for basically multiple driver, but definitely the multiple driver warning will come. I can give you an example. Uh, Multiple driver. So let's say I write data here also, and write Now this is multiple driver. This is also driving and this guy is also driving. Let's do the synthesis. How to resolve multiple driver? So basically, first of all, this is not allowed until the design requirement is there. Okay.
Mm.
So if it's not a in-out type signal, right? This is a not allowed. This is a mistake. Okay. And that's how it give us like warnings.
Mm.
Mhm. It is simulation log or what synthesis? Not saying, but it must be there. It should be there. Implementation. And this warning is a design SPDM as port data is driven by zero. See here, IO pop. Oh, already we defined as a maybe we defined as a in outright. That's why it's not showing the warning. Okay, we've just out type we define,
Mm.
and it will show us. So that's why it's not showing us. Because saying like it needs a this different. It's saying it's like IO port buffering is incomplete because in out is defined, right? So it's showing like you should expect both input and output buffering is needed. So what buffering is needs? It needs tri-state buffer to be added because it's data type in out.
Mm.
Okay. So how we have to add buffer? You know, means in the we have to add these buffers. This buffer in test bench and this buffer in because a read. So reading from inside. This should be in the inside here, and this should be in the test bench. Let's just do this. Okay. So just remove this. What we have to do whenever read is there, okay, when this is true, we take the data, else what we should read, else data should drive z. Okay. All bits should be Z. Okay, others impedance. Okay. Others maybe is giving a 32 bits. Okay. So do you think it's now it works in simulation? It will still not work because we are not driving from the test bench. Okay. So so let's take this as a write data. Okay. Let's declare some signal write data. Okay. Is not there. And we can say data gets write data. Okay. When write read is 1. Okay. Write read is 1. Basically, whenever writing. Okay. What is write condition? This is 1 and enable equal to 1. So when this condition is there, we write data should be write data, else be 32. 3, 4, 5, 6. Okay. So write data we have not defined. Let's define the write data. Right. This is a buffer. What of this buffer we are talking, right? This buffer we added. Let's do simulation. There's 31 elements. Acha. One Z is less. Where is this? Experience 71. We have 36. We've been 36 here. Yeah. You see? So this is a data port, right? So whenever writing, the write enable is there, and write data is there. Sorry, write is there, write enable is there. Then it's a write. So you see, data port is driven by this. Okay.
Mm.
Else, data is changing. Okay. And what is a read condition? Read condition is when the enable is there and the read is there. Write it is 0. So this is a read side. Why it is U? C is not written. Oh, that's why U is there. C is not, why is C is not written? Because write data we have not initialized. We have initialized to 0. Okay, I got it was the problem. It's not entered here and we are not driving. So let's make it read data. Okay. Buffer should be continuous driving. Okay. So we can make data here. Let's make it read data. This condition is true. Basically, this is a delayed one cycle delay. Read enable. Say read enable. Read enable condition is what? When the enable is 1 and not of this delayed one, right? Because data is coming here and we should drive this data on next cycle when the clock is done. So this is read enable condition, 1 clock delay. So we are delaying in the clock, and this is read enable we declare here. And read data also declare. Again, next data should be working. First data would have not be working. Next it would have working. It's still never written. Only lay. Okay. A buffer should be you coded in the clock, right? We should not code in the clock process. So I'll just explain it. So this is clock, right? Okay. And we are giving read enable. Basically, enable is here, and this is write. Okay, and we are changing the read write enable here, right? For one cycle. Okay,
Mm.
this is write and read. So basically, this should be sampled here, right? At the clock edge. So your actual read enable will be where? Your actual read data will come here at this cycle.
Mm.
So at this time we have to drive the uh, high Z, basically data. Otherwise, you should drive the high Z. So it
Mm.
means at this time, uh, we want to basically read the data. Okay, and otherwise, we should drive the high Z. Okay,
Yeah.
so that's why I delayed. Means we should know this. So I created a signal read enable, which will be like this. And at this point only, we drive the read data. That's why I created a read enable, which is like a delayed of this condition, enable and not of read, right? So this is a read enable, and read enable we should capture the next cycle, and at that time the read data will be available, and we should drive the high C. Basically, this bidirectional is not like is not easy to understand.
Mm.
Still, you see. So we write the high we can add more signals. We created some signal, right? It's evaluate data, right? So here we are writing, right? And read. So we are writing write data. We are driving the data whenever there's a write, and otherwise this guy is driving Z, right?
Yeah.
So on the data bus you'll be seeing miss this guy is driving Z. Read enable. Whenever read enable is there, not there, it will drive Z, right? On the data.
Yeah.
So that the test bench can drive it. So test bench can drive. So you see the data is appearing on the test bench.
Mm.
And whenever write is not there, so write is not there, right? So write is disabled here, right? It's read is there. So you see, and read is also not driving. So for times sometimes we are seeing the high Z itself because
Mm.
read data is available here, right? And then write data, and then this guy write is also not there because write is so sometimes you see high Z is available here,
Mm.
and but and here we are doing the read, right? So at the C time we are doing the read data. So read data is C. This data is there. So this is appearing here.
Mm.
See? And again the new data is driving. So here why we did not see the multiple driver here? You can say, right, this is right is there. It should give us some because both are driving the same data. When both guys drive the same data, then also contention won't occur, and we can see the same data appear. Because at this time we are driving the five C addresses there. Right? We are driving the C data, and then this guy is reading the C data. So that's why contention are there. You can see this contention. If let's say we read the D data instead of C data, we read the B data. You can see some contention here. Now you see contention is there. Why? Because we are trying to read the D. So data is D here, right? Read data is D1, and at this point of time, from here to here, this half period, read is also driving, right?
Mm.
And write is also driving because write enable is there, half clock. So it is like a contention. So contention is become red, X basically. And the bits which is same is appearing as one. The bits which is not which is different is appearing as X.
Okay.
Okay, so this issue is because like we are driving asynchronously from the test bench. If we drive the some signal which is related to clock, then it would have not created an issue. So this issue can be solved very easily if we just make the clock as one here. So basically, on the both will appear on the rising edge,
Mm.
uh, and then there'll not be any contention. So you just see. Basically, I made it like current in the current simulation. See, right is changing. The signal from the test bench is changing on the negative, right? Negative edge.
Yeah.
So if I do this change on the rising edge, so basically this read enable will also appear exactly here internally, right?
Mm.
So it will not show the issue. Let's see. Oh, it's a complete data contention because we are writing and reading together. Now it's like okay, we cannot. It changes some. Maybe we can remove this from the clock process just to show you. Okay. So now you see the data is appearing same time. There is no contention because at this time read is there. This read data is directly appearing here on the data, and at this time write is there. So it's write data is appearing. Okay.
Mm.
I hope this fight you would have understand some.
Yeah, it was little difficult, but I tried.
Yeah. RTL RAM is created and some see. So it's like a try. It's added the tri-state buffer. You see.
Mm.
So my- okay. So basically, we could not do a write read together if there is a like single data is there. So you must avoid writing and reading together on the.
Mm. Okay.
So basically, the condition when we are writing at the same time read should be driving Z, and when condition when we are reading the write should drive Z. Then the data will occur. So
Both
this
shouldn't happen
eh,
same time.
both should be complementary to each other. Enable basically.
Mm.
Okay, then we'll wrap up here.
Mm. Okay. So we'll
Then
do on Wednesday we'll do, or we'll do on Saturday.
this Wednesday we'll do, and from next time we will.
Mm. Okay. Okay. See you then on Wednesday.
Bye.
Yeah. Okay. Bye.